Okay, moving on to the second to last topic of this semester will be a discussion of stochastic growth models, the stochastic optimal growth model in particular, otherwise known as the Brock Mirman model. All right, so what I want to do starting today and over the next few class periods is to present just the baseline stochastic optimal or neoclassical growth model with complete markets. And I'll talk about what that means in just a minute. Of course, augmented, but what makes the model stochastic is we're going to have random productivity shocks embedded into the model. So the source of uncertainty is going to be a random element in the production function that causes the productivity of capital and labor to kind of bounce around over time, but given a known distribution. This model was originally due to Brock Mirman. You can find the paper in Blackboard, I believe, 1972. It's an important generalization of the Ramsey model for obvious reasons, but I think perhaps even more important is that this basic model provides kind of the starting point for most of the business cycle models that you're going to see in the next class. And certainly if you end up going into macroeconomics as your primary field. So the so-called class of real business cycle models that were developed in the, let's say, the early 80s and dominated the macroeconomic literature throughout the 80s and up even through the early 90s is basically an extension, can be seen as an extension of the Brock Mirman model. The new Keynesian business cycle models that were developed in the early 90s and used for the past few decades heavily is yet another extension of the real business cycle model. All of these things can kind of be built up from the Brock Mirman model, okay? What I'm going to do is try to present that model here and talk about some of its key implications. That is, its implications for its equilibrium, all right? Some of the properties of the policy functions that come out of it, and some of the properties of the long run equilibrium of this model. Now, just as a kind of warning here, in a model that has uncertainty, there's not going to be a thing called the steady state, right? In a deterministic perfect foresight model, what we've seen is that the economy will convert, under certain conditions, will converge to a fixed steady state in the long run. In a world with uncertainty, even as time goes to infinity, there's going to be a new realization of the productivity shock every period. And so you're never going to settle down into a fixed steady state. Instead, the kind of the analog concept that we're going to try to characterize is what's known as the long run stationary distribution of the capital stock, okay? The capital stock, you might imagine, and consumption will be functions of the productivity shock and equilibrium, right? The productivity shock has some well-defined distribution. Therefore, consumption and capital will also be a random variable, and they will inherit some of the distributional properties of the productivity shock. What we hope to find is that in the long run, over time, in what we would think of as the steady state, instead, this economy will kind of settle down to what's called a stationary or ergodic distribution for these variables like consumption and capital. Meaning that if we let T go out to a large enough value, we can predict that the capital stock will kind of bounce around within some particular distribution. And we want to be able to characterize what that limiting invariant distribution is. That's the idea there. So not a fixed point in the steady state, but a limiting invariant distribution, meaning that the distribution no longer changes through time. Okay, now let me talk a bit about this idea of complete markets. So the baseline growth model incorporates or assumes what is known as complete markets, okay? Now, what does that mean exactly? Households and firms in this economy can trade in a commodity that allows them to fully insure against any type of idiosyncratic risk or uncertainty that might prevail. Okay. Now, of course, we don't actually live in that type of world, but let's imagine for a moment that we did. Okay. All of us experience idiosyncratic risk all the time, right? Tavoy, if you had a job, you know that there is some possibility you might get fired from your job in any given week or any given month. Okay. That shock, that uncertainty is different from what Ben experiences. That's the sense in which it's idiosyncratic. Now, in a world where there are complete insurance markets, if we're all risk averse, what would we choose to do optimally? We would want to fully insure against the possibility of having any income loss from these idiosyncratic shocks. Okay. And so in these models, that device is assumed to be embedded in the model. And the type of insurance are what we call complete contingent claims markets, meaning that at time zero, you can purchase insurance against any possible future realization of uncertainty that may occur. Okay. So for some particular amount, you can purchase a claim to $1 worth of consumption at some point in the future if a particular state of nature occurs. All right. In that way, everyone would want to fully insure against any type of uncertainty if markets were complete. All right. Now, we obviously don't live in a world where we have complete insurance markets. In the real world, insurance markets are incomplete. You can partially insure against future shocks, but not completely. All right. Think about what the implications of that would be, though. If you could fully insure against any type of idiosyncratic risk, then the only shocks that would matter for economic fluctuations would be aggregate shocks that affect everyone, like productivity shocks, as opposed to particular shocks to your own employment. As a result, in the Brock Mirman model and in this class of optimal growth models, we don't even talk about idiosyncratic uncertainty. The only type of uncertainty that is interesting from the viewpoint of these models would be aggregate uncertainty, like shocks to technology or shocks to government spending or taxation. Okay. If, however, there were incomplete markets or partial insurance, then idiosyncratic shocks matter. But that gives rise to a very different class of models called heterogeneous agent models. We are going to be working in this class within a family of models called a representative agent model. Okay. Again, these heterogeneous agent models are really, really interesting. And the existence of incomplete markets gives rise to a whole new set of implications and properties on these models that are very much in the discussion of the current macroeconomic literature that's being published right now. Okay. In fact, I'm working on some stuff that looks at incomplete markets in the context of a new Keynesian business cycle model.
Are fully complete markets like optimal? Is that what?
They're optimal. They're optimal if agents in the economy are risk averse. Yes. Anyone who's risk averse is going to achieve higher utility under full insurance than partial insurance. But we know that full insurance is not a realistic assumption to make in order to match what we see in the data. For years, however, several generations of macroeconomic models assumed complete markets because they're more analytically tractable. Okay, but it's only been recent where the computational tools have been kind of developed to harness the power of those numerical techniques to address these heterogeneous agent models more effectively. But we're gonna do first things first here and talk about the representative agent model. So the source of uncertainty will be aggregate shocks rather than these idiosyncratic shocks. But underlying all this, I want you guys to realize that what's happening in this model is that there are agents in the model that have access to these complete set of contingent claims markets where they can buy and sell securities in a way that perfectly insures them against any of this potential idiosyncratic risk. So the only risk that we're going to talk about is the aggregate risk coming from technology shocks. So that's a short discussion of those issues. I would encourage you to get a better understanding of it, to read the relevant section in your textbook. It goes into much greater detail about these underlying assumptions. Okay, so let's set up the Brock Mirman model first. So this model basically focuses on the optimal growth problem of a benevolent social planner in a dynamic kind of neoclassical environment with uncertainty. Now, since we are dealing with a perfectly competitive world where there are no frictions or informational distortions or externalities, then we know those welfare theorems are going to apply. And so the allocations that are identified by the benevolent social planner will correspond or can be supported in a decentralized competitive environment. Remember that key proposition we studied earlier that showed that the allocations of the optimal growth model are the same as the ones that prevail in the Ramsey neoclassical model? Same idea is going on here. So what we're talking about really is a competitive environment, but those allocations correspond to the ones that a benevolent planner would choose. And so we're going to solve this model from the perspective of a benevolent social planner. That's what the Brock Mirman model does. And again, within that framework, there are complete contingent claims markets. That's part of the underlying environment there. But again, we don't have to discuss that analytically, because agents will perfectly insure against idiosyncratic risk. So only the aggregate shocks will actually matter. Okay, let's talk about production first. There is going to be an aggregate production function in this economy, where all perfectly competitive firms have a similar production function. And so we can think about aggregate supply in this economy coming from one large production function, which says that output at time t is a function of the capital stock at time t, labor supply at time t, as well as the state of productivity, where zt, again, is going to be some element of some set capital Z, which takes on finite number of possible values, with Z1 less than Z2 less than Zn. So they're written in ascending order. So Z is going to be interpreted as a stochastic productivity term that affects how much output is produced for given amounts of capital and labor. It has a natural kind of economic interpretation to it. And it takes on this discrete topology. We will further assume that ZT follows a monotone Markov chain. All right, now what does that mean? If Z follows a Markov chain, then the probability that ZT is equal to, let's say, some ZJ, conditional on the full history of Z's up through period T minus 1, is going to be equal to what? That's equal to the probability that ZT is equal to ZJ, conditional on only what Z was in the previous period. All that matters for determining the conditional probability of Z at date T is what Z was in the previous period. We don't need to keep track of the full history of Z's through time. And this helps us characterize the distribution of the productivity shocks using the transition matrix, right? What does Qij mean? That's the probability that ZT is equal to ZJ, given that ZT minus 1 was equal to ZI. All right? The various rows of the transition matrix Q characterize the conditional distribution of the Z's over time. Okay, now what do we know about the production function F? Continuing on the theme that we've developed all semester, we're going to assume that F is neoclassical. That is, it satisfies assumptions 1 and 2 from our discussion of the Solow model. What does that mean? The marginal returns to capital and labor are positive. So the first derivatives of F with respect to capital and labor are positive. However, they're diminishing. So the second derivatives are negative. So the production function is increasing in capital and labor, but also strictly concave. What else do we know about the neoclassical production function? Really important assumption. It is linearly homogeneous, right? In other words, if we multiply the amount of capital and labor by some scalar, some factor, lambda, it ends up multiplying output by the same factor, lambda. It's linearly homogeneous. That's important because it has enabled us to rewrite the model in intensive form. That is in terms of its per capita variables, right? So 1 over LT times YT is equal to 1 over LT times F of K L Z, which is just equal to F of K over L, L over L, and Z. Remember, it's linearly homogeneous with respect to just the first 2 arguments. Y over L is output per worker, little y. So that's equal to F of little k and Z, since L over L just goes to 1. So output per worker in the Brock Mirman model can be written as a function of capital per worker along with the productivity shock. So the productivity shock tells us how, or a change in the productivity shock changes the relationship then between capital per worker and output per worker. Now, we're going to make an assumption here that is critical. And that is that larger values of the productivity disturbance correspond to greater levels of output. In other words, for Zj bigger than Zi, it's going to imply that F of K Zj is bigger than F of K Zi for all K on the positive reals, where J, of course, is bigger than I, since the Z's are expressed in ascending order. We can't take derivatives of the production function with respect to Z because Z is a discrete random variable. But the production function is going to assume to be increasing in Z. So higher values of the productivity shock boost output for a given amount of capital per worker.
Is that holding time constant?
Yes.
Yeah.
Yes. Okay, questions about that? Let's talk about preferences for a minute. The economy is going to admit a representative household with an instantaneous utility function given by U of C that satisfies the same assumptions we talked about in the context of the neoclassical model. So U will map elements from the positive reals into the reals. The marginal utility of consumption is positive, and it is strictly, the marginal utility of consumption is strictly decreasing. So utility exhibits diminishing returns to consumption for all C in the positive reals. Now again, The economy represents or admits a representative household here because there are these complete insurance markets, right? Which allow individuals to perfectly insure against any type of idiosyncratic risk. Let me see if I can explain this a little bit better because I'm seeing some confused looks. So, Ben, imagine that there's incomplete markets, okay? You know that that you can get hit with an earnings shock in any given future period. And as a result, what you're going to do then is you're going to save some of your income over time in order to more or less self-insure against the possibility of losing your job or having an earnings reduction, okay? Well, everybody else in the economy also experiences different types of risk. And so they also are going to try to self-insure. But what that means then is that everybody's consumption and savings decision is going to depend on their full work histories and the full realization of those idiosyncratic shocks over time, right? If you lost your job last period, but Tavoy didn't, you're going to have different consumption savings decisions today. We're dealing with a heterogeneous agent world. But with complete markets, provided you guys have the same utility function, you're going to perfectly insure against those outcomes and have the same consumption every period. That's a representative agent model, where the only source of uncertainty that will matter for equilibrium will then be these aggregate shocks that you can't insure against. Okay. The representative household, just like in the neoclassical world, is going to supply 1 unit of labor inelastically to the workforce every period. And I'm also going to assume that just for the case of simplicity here, that there's no population growth. So N is equal to 0 in this model. And so I'm just going to let LT be equal to 1. I'm going to normalize it to 1 for all time. Now, why is this helpful? Because then capital per worker is just equal to aggregate capital, right? And consumption per worker is just equal to aggregate consumption. Same for output. So when we get rid of population growth, essentially what that means is that the per capita variables are indistinguishable from the aggregate variables. There's no distinction between them. It's just for mathematical simplicity. What else? Recall from our earlier discussion where we introduced the stochastic growth model that consumption as well as your investment and savings decisions at each date t are made after learning the realization of the stochastic shock. So in every period, CT is going to be some function of the history of shocks leading up through period T. And the capital stock that we carry into the next period will also be a function of the shocks up through period T. Capital in period T plus 1 will not depend on the realization of the shock at time T plus 1. It's going to be predetermined 1 period in advance based on our consumption and savings decision. Okay, what does the representative household do in the Brock Mirman model? They are interested in maximizing over sequences of consumption and capital from 0 to infinity, not discounted lifetime utility, but rather the expectation of discounted lifetime utility, conditional on information that is known at the beginning of time, date 0, subject to the period by period resource constraint for the planner, which says that KT plus 1 has to be equal to f of KT ZT plus 1 minus delta KT minus CT. where KT has to be strictly greater than 0 every period, and K0 and Z0 are given and known when the planner makes her decisions. Now, again, there's two important points to notice here. One is that this conditional expectation is evaluated over all possible realizations of the shocks over time. So in the Brock Mirman model, at the beginning of date 0, once the planner has observed the initial endowment of capital and whatever the initial realization of the shock is, she wants to maximize expected discounted lifetime utility. And she doesn't know what the sequence of shocks is going to be, that is Z superscript T, but she does know the distribution from which they are drawn, and so can correctly form this conditional expectation. Another point I want to make here is that you'll notice that the resource constraint has to hold for all dates T, as well as for all possible states of the world Z. Okay, so regardless of what sequence of technology or productivity shocks plays out, the resource constraint must be respected every single period. Now, what would, if the planner tried to solve this model using the sequence problem, what would she do? She would try to find an infinite sequence of these state contingent plans for capital and consumption. Right? And of course, that is difficult to do. We saw that in the last section, that even just for 2 possible values of the shock and 3 periods, the number of different paths that the planner would have to consider is 8, right? So the number of possible paths for the technology shock grow enormously with the size of N as well as the time horizon. So trying to characterize the solution to the sequence problem is analytically a difficult thing to do, right? What has always been our strategy from the get-go with these types of problems is not to solve the sequence problem, but to solve a different problem whose answer will be equivalent to the sequence problem, and that is the functional equation. So let's write down what the recursive representation of the Brock Mirman model looks like. Now you guys should hopefully be starting to understand this a bit better. What does that look like? Instead of the sequence problem, what does the Bellman equation, that is the recursive formulation of the Brock Mirman problem, look like? Well, on the left-hand side of the equation, we have what? Left-hand side. Value function, which will depend on 2 things. The state, that is the existing capital stock, and to avoid what else? The stochastic term Z, right? That's equal to the max of the sum of 2 terms, right? The first is the optimal current return, right? That's utility evaluated at the current value of consumption. Now, what we've done thus far is to use the resource constraint to substitute that into the utility function. So that would be what? F of kz plus 1 minus delta k minus k prime, where k prime is going to be our control variable, right? Plus the discounted value of what? The expected continuation return. Be careful, the expected value of V of K prime, Z prime, conditional on what the planner knows about the current realization of the shock, Z. And this is the Bellman equation that looks exactly like this for any possible realization of the current shock Z. Now we're almost done. Maximization occurs by choosing the optimal value of tomorrow's capital stock, right? And not just any value of K prime can be chosen, but rather it's constrained by something. It's constrained by this set valued mapping G, which we call the constraint correspondence, that depends on the current stock of capital and the current realization of the shock. Now the question is, what does G look like? What is the constraint set here?
The set between consuming everything and consuming nothing.
If you consume everything, then the amount of resources you have for next period's capital is 0. If you consume nothing, then the amount of capital you have to carry into the next period would be F of KZ, that's the output you produce today, plus whatever is left over after capital has depreciated. Perfect. There you go. So this is the recursive statement of the Brock Mirman model. Instead of dealing with the sequence problem, which is horrible and nasty, because we have this infinite sequence of state contingent functions or plans for consumption and capital, we can write it succinctly as a Bellman equation, where instead we're just solving for the policy function K prime, which shows how the optimal value of K is determined by the current value of K and the current value of Z. Okay. This leads us to proposition 1. Which I'll just read. And it says that in the Brock Mirman model, the value function V is uniquely defined, strictly increasing in K and Z, strictly concave in K, and differentiable in K. Moreover, there exists a uniquely defined policy function such that the capital stock is given by K prime is equal to pi of KZ. What is this proposition, or what do you guys suggest we do to prove this proposition? What does it sound like the strategy should be?
Is the same strategy that we've been using?
Yeah, right. I mean, how do we prove what it's saying is that the value function exists and is unique. That's theorem 2, I believe, right? Or no, I'm sorry, is it theorem 3, I believe, right? Which follows from what? The state variable lives on a compact set of the reals, or the state variable resides on a compact set. The utility function is bounded, right? The objective function exists and is finite, et cetera, et cetera. Now, we showed all that stuff in the deterministic world, all right? I'm not going to go in any enormous detail here through this. What I want to do is show how a few of the things are modified to account for uncertainty, but I'm not going to go step by step in demonstrating that every single one of those assumptions holds, all right? There's no need to do that. You guys can kind of work through those and read through them on your own. But the point here is that the way you would prove this formally is that you would go through and show that the Brock Mirman model satisfies those various assumptions. And if it does, we know that the value function exists, it's unique, that a policy function exists, it's also unique, that the value function is strictly increasing in both of its arguments, strictly concave, et cetera, okay? So let me, instead of proving that step by step, let me just go through some of the key points there that need to be adjusted somewhat to account for the fact that we have a stochastic productivity term now, okay? So what was the first thing that we wanted to show in order to get the existence and uniqueness of the value function? It's that the state variable, the relevant state variable in our model, the capital stock, has to live on some closed and bounded interval, right? So that without loss of generality, we can restrict the capital stock to living on a closed and bounded set. That is still going to hold in this model, despite the fact that we have random technology shocks. Okay, so let's just work through that really quickly. What was the strategy involved there? We know that the capital stock can never be less than 0, but it has to be bounded above by something. It has to be bounded above by some kind of maximum sustainable capital stock in the model. And we found that by simply assuming that consumption is equal to 0 forever, right? Well, let me also throw in another thing here. To really determine what the maximum level of capital is in the long run, you also need to not only think about what would happen if consumption was 0 forever, but also if the technology shock just happened to be equal to its highest value every single period. So what if every period our draw of the productivity shock was equal to Zn? That's possible. It's not likely, but there's some probability that that would occur. What would eventually happen to the capital stock here? Well, simply go up to the resource constraint and we would find that KT plus 1 would be equal to F of KT Zn plus 1 minus delta times KT minus 0 for consumption. This implies a mapping between KT and KT plus 1, right? If we were to graph the two portions of this mapping, what does it look like? The first part is the production function, right? So this is F of K for some particular value of the shock, Zn. Hold on. I need to evaluate this in a steady state first. Not the steady state, but the fixed point. So if Z is equal to Zn forever, then this defines a mapping between KT and KT plus 1, right? Well, what eventually will happen? That the capital stock will converge to some fixed point. I don't want to call it a steady state because that implies an optimum, right? But it's a fixed point that would be this kind of maximum sustainable level of capital given by, let's call it K bar. That's K bar would be equal to F of K bar Zn plus 1 minus delta times K bar. Cancel, cancel, and you would get that F of K bar Zn has to be equal to delta K bar. K bar is implicitly defined by this condition, where the production function intersects the depreciation schedule. Hopefully that makes sense. If we consume nothing forever, and we generate the highest possible value of the technology shock every period, the capital stock is going to accumulate over time up to a point where every additional unit of output we produce is just barely enough to offset depreciating capital, right? Output increases, but at a decreasing rate. Depreciation increases at a constant rate. So at some point, diminishing returns sets in, and everything we produce every period is just enough to offset depreciating capital. That's this K bar term. That's this maximum sustainable level of capital. Okay. Now, how did we argue this before? If KT is less than or equal to K bar, I'm sorry, if K0 is less than or equal to K bar, then KT will be less than or equal to K bar for all T, correct? It's never possible then for the capital stock to exceed K bar. But what happens if initial capital is actually bigger than K bar? then what's going to happen? If initial capital is way over here, then depreciation will be bigger than output and the capital stock will decline, correct? And so if K0 is bigger than K bar, then what that means is that KT will be less than or equal to K0 for all T. So without loss of generality then, we can assume that the capital stock will reside on this closed and bounded interval where the lower bound is determined by 0 and the upper bound is determined as the max of either K bar or initial capital, whichever of the two happens to be greater. That is a compact subset of the reals. What happens here if we get a smaller realization of the productivity shock? So Z n minus 1. The whole production function shifts down, right? And why do we know that? Because of an assumption that we made, that the production function is increasing in the technology shock. So the highest sustainable possible level of capital in this model is the one where f of k Zn is equal to delta k, defined implicitly as this K bar. The capital stock is either going to be strictly less than that forever or less than initial capital if initial capital happens to be bigger than K bar. And so without loss of generality, we know that the basic constraints on the problem are enough to ensure that the main state variable here resides on a closed and bounded interval. It resides on a compact set of the reals so that we can apply the first of our dynamic programming theorems. Okay. That was actually the second assumption in our list of assumptions that we went over a few class periods ago. What was the first assumption? It had a few parts. One was that the constraint set was non-empty. In other words, the planner has to have some menu of options to actually choose from. The constraint set cannot be the null set, right? Now that's obvious. This is obviously going to be satisfied because delta is between 0 and 1, right? If delta could be a lot bigger than 1, for instance, then it's possible that the upper bound here could be a negative number, in which case you've got the null set, right? So because delta is a fraction, this is going to be some positive number bigger than 0. So G is going to be non-empty. That's going to be fine for any possible value of K on its feasible set. The other important part of that first assumption was that the limit as n goes to infinity of the expected value of lifetime utility, so from t is equal to 0 to n, beta to the t, u of f of k zt minus 1, comma zt, plus 1 minus delta k of zt minus 1, minus k zt plus 1, that is k of z superscript t, conditional on z0, exists. the lifetime objective function has to exist in order for the planner to actually maximize it, okay? Demonstrating its existence is pretty straightforward once we demonstrate that the capital stock resides on a closed and bounded interval, okay? Now, how do I know that? Take the period utility function. We know that that has to be less than u of f of k zt minus 1 zt plus 1 minus delta k of zt minus 1. In other words, if we get rid of kt plus 1 from inside the utility function, the value of utility is going to be higher. Why? Because k has to be strictly greater than or equal to 0, and u prime of c is positive. So making consumption bigger is going to increase the value of utility. But this can be bounded above by recognizing that the highest sustainable value of k is given by some, let's call it k hat, where k hat is defined as the maximum of this k bar and k0 that we talked about earlier. The production function is increasing in capital. 1 minus delta k is also increasing in capital. And so that means that utility should be bounded above by this term. But then this can also be bounded above by recognizing that the highest value of production then occurs for zt is equal to zn. If k lives on a compact set and z takes on a discrete topology, so it's compact by construction, then that means the utility function is going to be bounded because it is a continuous function defined on a compact domain. So period utility is bounded by some, let's call it u bar, that has to be less than infinity. All of this implies then that the value of pursuing an optimal sequence of state contingent plans over time for the planner has to be less than or equal to, let's see, u bar over 1 minus beta. If I substitute u bar for my utility function in this discounted conditional expectation, it just becomes u bar times 1 over 1 minus beta, which we know has to be finite. And so the lifetime objective function actually exists. Demonstrating those is enough to prove the existence and uniqueness of the value function in this stochastic environment. And I'm going to stop there. So here's what we're going to do at the start of next class. I'm not going to go over the concavity proof. I'm just going to restate it to make sure you guys understand it and what it means for the constraint set to be convex. This is enough to guarantee the existence of a unique optimal policy function, pi. The utility function will be increasing. The constraint set will be monotone in K. That's enough to prove that the value function will be increasing in the capital stock. The only other things we're going to have to do that would build on what we did earlier is show that a couple of those assumptions regarding the random variable z are going to be satisfied, okay? If you guys remember in the last class, I think it was the last class, one of the theorems states that the value function is monotonic not only in the state x, but also in the random variable z. We want to show that the Brock Mirman model satisfies that theorem as well, because it's going to be important when discussing certain properties of the solutions of this model. So we'll work through those assumptions. They're pretty easy to do. And then what I would like to do is actually take a step back from this version of the model for a moment and look at the canonical version of the Brock Mirman model. What's that? That's one that has log preferences and Cobb-Douglas production and full depreciation. What is the advantage of doing that? It allows us to find analytical solutions like you guys did on your exam. So we'll work through the analytical or the canonical version of the Brock Mirman model to solve for the policy function and the value function. And then we'll come back and look at a couple of the key properties of the general Brock Mirman model over the next 2 class periods. Okay?